Hi guys, welcome to today's video. I'm gonna go through amide today. So this is another function group as a carboxylic acid derivative. So this amide function group, so as you can imagine, it's very similar to amine, so you must have a nitrogen. So this has a function group of CON, and this nitrogen can literally bond to anything. Okay, you can bond to H's, you can bond to carbons. Well, not literally everything, but it's normally H's and carbons, for example. Okay, so let's just go through the naming, and this could just be whatever. Okay, so let's just go through the naming. Don't forget that carbon only bonds 3 times. So let's have a look at this. So if I give you something like that, so just like all carboxylic acid derivatives, I'll just give you something really simple. This carbon is by default number 1, and then you just count 1, 2, 3, and this will give us propan, and then the suffix is just amide, so just propanamide. Okay, nice and easy, propanamide. You don't need to say one propan 1 amide or 1 propanamide, because this carbon with a COH is by default carbon number 1. Okay, so propanamide. However, this can be a little bit tricky. Now, in this case, this is what we call a primary amide. Now, why is this a primary amide? Because your nitrogen is only bonded to 1 carbon. Okay, so you can have secondary and tertiary amide, which will come into play when we do spectroscopy later on. So let's just keep the same thing. Let's just have our propanamide, but instead of having a hydrogen, 2 hydrogens, let's just put a CH3 there. Okay, so this changes, well, it doesn't change everything, but it changes something. Okay, so we're still interested in the longest carbon chain, which is that bit there. So this is my longest carbon chain, 1, 2, 3 carbons, and I have my CON, so that's my amide. So it's still propanamide, because that's the most important part of this molecule, right? Propanamide. But then I have got this CH3 thing lying around. So this is a methyl group, okay? Because it's discontinued from the chain. Because this is a nitrogen, it's not a carbon, so it's not a, the CH3 is a branch. So it's just 1 carbon, so this is methyl. Okay, so where is, as you will know from now, how do we do naming? The naming of of this particular methyl group, normally we do numbers like 1, 2, whatever, referring to whatever carbon that this nitrogen, this CH3 is bonded to, but this CH3 is attached to the nitrogen. So this is called N-methyl propanamide. So if you translate this, I have 3 carbons in the longest chain. So this is 3 carbons in the longest chain. Amide means I have a CON. Methyl means I have a CH3. Where is it? It's bonded to the nitrogen. Bonded to nitrogen. Okay, so that's N-methyl propanamide. So this is a secondary amide, because my nitrogen is bonded to 2 carbons. And as you can imagine, I can have tertiary amide. So let's just do that. So instead of having, let's just do it like this. Instead of having the nitrogen bonding to any hydrogens, I can have a methyl group, I can have an ethyl group. Okay, so how do we name this? So still, we look at our longest carbon chain with the CON attached, because that's our most important part. It's still propanamide. And then we have got an ethyl group, we got a methyl group. So this is called N-ethyl propanamide. Okay, so the ethyl group, the CH2CH3 is bonding to the N, the methyl group is bonding to the N as well. So it's N-ethyl N-methyl propanamide. So you just need to, think about it. The naming is not confusing. The suffix is amide, and then you look for the longest carbon chain with the CON as a function group, and then whatever the branch, you can just name it afterwards. Okay, nice and simple. So the one really important thing that people need to understand with the amide last year we talked about the amine. So amine is just, you have a carbon bonding to a nitrogen. So amine are alkaline. So this is a weak base. Okay, so this is a weak base, which means it partially dissociate. Okay, but amide, it's so weak in terms of its ability to react as a base. Is so close that we just say it's neutral. So close to pH 7, we just say it's neutral. Because it doesn't really, because of the presence of the carbonyl group and everything else, it doesn't accept another hydrogen. It can't accept another hydrogen. Okay, because of the fact the carbonyl group is nearby, it just really limits a nitrogen's ability to accept another hydrogen, because that's what bases do. The bases accept another hydrogen, but in this case it can't, so it's neutral. So that means, if you think about the distinguishing test, this works with litmus paper, yay. This one with litmus, and it doesn't do that. Okay, it doesn't really react. And your amide is normally, if you look at the structure of this amide, the amide is normally something that has really high boiling point and melting point in comparison to the other organic functional group. Why is that? Because you got you got hydrogen bonding here, you got a carbonyl group over here, you got a big molar mass, so you got all three of the intermolecular forces. But amine is not too shabby in terms of that as well, because it also has hydrogen bonding. So it tends to have high boiling point, high melting point in comparison with something like a haloalkane, for example, that has similar sort of molar mass. Okay, but this is just amide. And how you can make amide, I kind of talked about it in the acyl chloride video. I'll just do that really quick. But how do you produce an amide? One of the method is, let's just keep going to our propanamide. Why not we? So if I want to make propanamide, so the thing that I need to do, NH2. The thing I need to do is I need to use NH3, because that's going to, one of the things that we don't really ask this in exam, but you can see that this is acidic. Ammonia in this case is alkaline. So this is acidic, this is alkaline. So you actually have a neutralization reaction. Okay, so one of the intermediate, I'll just do it down here. Normally we don't require you to do this, but this is what happens when you have them reacting with each other. So it becomes COO-NH4 plus, NH4. Okay, so this is COO minus, this is NH4 plus, and because by definition, an acid will donate the hydrogen to the base, and this is what we form. Okay, and then what it does after that, and then you need to, you make the ammonium salt. So this is a salt, because just like NaCl, this is NH4 plus CH3 CH2 CO minus. It's a salt. Okay, so what you can do is you can just heat this salt and causing it to dehydrate. You're removing water out of this. So if you think about that, we're removing water. I'm removing two H's and one of the oxygens to make water, and the remaining molecules will stay behind, and then they will become an amide. Okay, so you can see this is two H's, this is two H's, that's where my four H's come from. So the heat really takes away the water, it dehydrates it. So if you want to write it in short, it's just carboxylic acid plus ammonia plus heat, and then you make the amide and water as a byproduct. Okay, so this is just neutralization reaction that just becomes a salt, and then you heat the salt to get the amide. Okay, because you're removing water out of it. Now the other thing that you can do, let's say you don't have to use ammonia, and the other part, let's say if I just make this thing again, you don't have to use ammonia, you can use an amine. And this is where the part I keep mentioning about year 13 about this particular part of chemistry is that you can literally just copy paste. You just need to understand what's happening here. Okay, so we're not going to go through the salt stage again, but you will know that this is essentially just combining two smaller molecules together. So this OH, you can think of that OH, and this H, they went to make water. Okay, and then the rest of the molecule went to join together. So you just copy paste. It doesn't matter what's on this side. You literally just copy paste it, and then you have got an amide. And how do we name this amide? This will be N-ethyl propanamide. Okay, so that's how you can make an amide. The other way that you can make an amide is by using acyl chloride. So if you have, say, something like CH3COCl, this is ethanoyl chloride. If I react this with what's that thing majiggy called? You just anything, just ammonia, for example. So we talked about this in my acyl chloride video. Your nitrogen just gonna attack this carbon, and then it's gonna kick out the H, and the other one's gonna kick out the Cl. And then you have a nucleophilic substitution, then you made amide. Okay, so you don't need heat. You can just work without the usage of heat. Or you can just, like I did with the other one, you can just literally, again, copy paste, same sort of thinking. This Cl and this H, they need to go make HCl, and then the rest of the molecules simply combine together to give you, so you just copy paste again, just make sure don't make a mistake, just copy that, and then you have made an amide. Okay, no reagents required. You make HCl as a give off byproduct that allows you to distinguish this reaction well, because it makes white fume and da da da. Okay, so that's how you make an amide. And the amide itself, it's very, in terms of the more chemistry that we do, the amide, the amide link, the peptide link, this is more to do with polymers. The CON link is one of the most important links in biochemistry, because that's essentially in all of our cells. If you look at DNA, proteins, and all that sort of wonderful stuff, amino acids, this is a link that's holding everything together, the CON link. Okay, so that's really important. Now, so that's how you make an amide. All right, so you just combine acyl chloride or carboxylic acid, you make an amide. Same as how you make an ester, you use carboxylic acid or acyl chloride to make an ester. But similar to ester, the part that we need to emphasize on is hydrolysis. Okay, so hydrolysis of amide, and this is something that if you watched my old exam videos, and this is something that I would highly recommend every student to do if you're struggling with this particular concept, because it can get really, really long and tedious and intimidating. But hopefully that's why I do this, to make your life a little bit easier. So we have the CON link, right? I don't care about the H. We got the CON link. So if we do hydrolysis, what's hydrolysis? Hydrolysis is the breaking of the longer molecule into two smaller molecules by using water. So you're inserting water into this molecule, right? So the first thing that you should always do, and whenever you see COO or CON, just grab a pencil, grab a pen, just draw a line there, okay? Because if that molecule was to break, that's where you can, cleave the larger molecule into two smaller molecules, and then you can find out and then you just copy paste. Okay, so we're not really interested in the COO yet, because with my class I've already done it. I can do another video for other people, but it's the same concept. All right, so you say if I do let's say if I do acidic hydrolysis. Okay, let's say if I do acidic hydrolysis. So what it means is that I'm adding H plus and water and heat. Okay, so I'm doing acidic hydrolysis. So what's going to happen? You are just going to copy what we cut it in half. You're just going to copy what's on the left, and then what's on the right. Just copy it as you see it. You don't need to change a single thing yet, just copy it. Okay, because this method I call the triple C's, you know, the 3 C's. The copy, you copy, you sorry, not copy yet, you cut, you first cut it, cut, you copy, you complete. Okay, so you cut it, you copy it, you complete it. Okay, so if we're gonna cut it there, already done that, so we're gonna copy that, and we're literally just gonna copy as it is, which we've done. And then this is where you need to think about what we're doing. So we got water here. Water is made of H2O, which is OH and H. Okay, so this is where the complete part comes in, because this is incomplete, this is incomplete. What is one functional group that you knew that can do with an OH? So this is your carboxylic acid, and this is your amine. Okay, so that's your 2 products, and if you can do that, you already got some points. Okay, but this reaction's incomplete. Why is it incomplete? Because you need to understand that we are doing this in acidic condition. So that means in the solution, you have a lot of H plus lying around. And when you have a lot of H plus running around, this is going to undergo further neutralization reaction with your 2 products. Okay, well, in this case, just 1 product. So if we look at this guy, this is propanoic acid. This is acidic, right? If this is acidic, this is not going to react anymore. This is just going to stay exactly as it is. But then, if we have look at that, this is an amine. This is an amine, which means this is a base, and the other guy is an acid. So this is going to further neutralize. This is going to further neutralize, and you are going to produce. How does a base react? Is that it's going to gain another H and gives us a +1 charge. Okay, so the 2 products is this one that I'm highlighting right now, and this one I'm highlighting right now. Okay, so how does it do that? Because we made an amine, and amines are alkaline, so they can be further neutralized by the acidic condition. Okay, so if I do the same reaction, where are you, CH2? If I do the same reaction, but now I've changed it to, you know, so just again, get into habit. You see that you've just cut a line. What if I do this in basic condition? Okay, so for example, sodium hydroxide and water and heat and heat it up. What's going to happen here? So it's the same thing. You cut it. I already done it, and then just copy. Okay, just copy it, and then just copy exactly how you see it. All right. Now what do? Same thing. This is water, so we're just gonna put OH here. We're gonna put H here. Exactly the same thing. Okay, but then you need to come back into this and go, hold on a minute. This is a base. Thus, COH is an acid. So this is acidic, and that is the NaOH is a base. So they are. So the moment you produce some carboxylic acid, you are going to lose it because it's going to neutralize. So how is it going to neutralize? It's just going to go, how does an acid react? It's just going to lose this H. It's going to lose this H. So it's become COO minus. Or in this case where I gave you sodium hydroxide, you can write it like that. COO minus Na plus, or you can just delete the signs, you know, COO Na as a salt. Okay, so this is the product that we produced, and this is the product that we produced, because this guy doesn't react anymore. Because it's already this is already alkaline, and this is alkaline, so it's not going to do anything anymore. Okay, so that's the hydrolysis of an amide. So you just remember, whenever you see the CON, you just cut it, copy it, add the things at the end, and just ask yourself, okay, so what condition is it? Which one of these 2 is going to further neutralize? Because depending on the condition, only one of them gets neutralized. Okay, so you can, in terms of distinguishing tests, which is not easiest thing to do with amide, because what you could do is, like, say if you have a simple amide like this, how do you distinguish it from something else? Because it's not, it doesn't really react with anything, to be honest. It's not very reactive. So how do we distinguish it from other things? You can do basic hydrolysis. Okay, you can do basic hydrolysis, and then you make CH3COO minus. It's actually COONA. So same thing. I'm not going to rewrite that again, and you're going to make some NH3. Okay, because you're going to cut there, and then this NH2 becomes NH3, and then you can technically smell this, because ammonia is, it concentrated ammonia. If you take a deep whiff of that, oh my god, you're gonna feel it. I'm telling you that it does not smell pleasant. So you can test for this NH3, but the thing that people always get confused, they could just go, oh, I make NH3, I'm just gonna use litmus paper in there, I'm just gonna put some real litmus paper in the solution, and then that should turn blue, right? It should turn blue because I made ammonia. That's the base. That's what I've been learning in class. But then you may have forgotten that this NaOH is also basic. Okay, so your red litmus paper will definitely turn blue. And how would you know that it's not because of the NaOH you have already sitting in there, or it is the ammonia that you produced? You can't tell. All right, so that's how you can. The litmus paper is really not the best method, because you already have the NaOH as a catalyst or ingredient that's in the solution that's causing the reaction to occur. It's not going away. You still have some sitting in there. So how do you know that your red litmus paper turned into blue? Is not because of the sodium hydroxide. You can't. Okay, so normally, the amide hydrolysis, the distinguishing test is not the easiest to do. We normally just go for the smell of the ammonia, but other than that, you can't really distinguish it that easily compared to something like alkane, aldehydes, and so on and so forth. Okay, so the key thing with amide, just remember, is basic. It's not base at all. It's so weakly basic. We say it's neutral. The hydrolysis of amide is important, and then how you produce amide from the carboxylic acid and the acyl chloride, which is very similar. Different types of reaction, but very, very similar in terms of the end product. Okay, so hopefully this is helpful, and I'll see you guys next time. Bye-bye.